The rhythmic hum of modern agriculture conceals a fascinating story about one of farming's most ingenious inventions. Every day, millions of farmers around the world rely on a mechanical marvel that transformed how work gets done in the fields. Yet most people have never stopped to consider its existence. What is this hidden hero of agriculture, and why did its invention change everything about farming as we know it? Before we can understand this revolutionary device, we need to transport ourselves back to a time when farming was brutally difficult work. Picture the 1800s, when every task on a farm required either human muscle or animal strength. Farmers would spend entire days accomplishing what we can now do in mere hours. The question that haunted every agricultural worker was simple yet profound. How could anyone harness more power without requiring more horses, more oxen, or more exhausted human bodies? The answer began to emerge with the arrival of tractors in the late 19th and early 20th centuries. These mechanical beasts promised to revolutionize agriculture by providing consistent, powerful energy that didn't need rest or food. But here's where things get interesting. The earliest tractors could pull implements across fields, but they couldn't do much else. They were essentially mobile engines on wheels. So another question arose. If a tractor had all this power sitting there in its engine, why couldn't that power be used for other things besides just pulling? By the way, if you're passionate about these stories of engineering, strength, and industrial heritage, here you'll discover documentaries about legendary tractors, colossal machines, and the equipment that transformed agriculture, mining, and construction. Subscribe, and every week we'll explore together how these machines change the world and the way we work. Farmers quickly realized that their fields required more than just pulling power. They needed to operate grain threshers, water pumps, sawmills, and countless other machines. The conventional solution was to use belt drives. Workers would position the tractor near the equipment, then connect a long belt from a pulley on the tractor to a pulley on the machine. This worked, but it was dangerous, inefficient, and frustrating. The belts would slip, break, and require constant adjustment. People lost fingers, hands, and sometimes their lives when clothing got caught in these exposed spinning belts. There had to be a better way, but what would it look like? The breakthrough came from understanding a fundamental principle of mechanical engineering. Power doesn't have to be transmitted through visible, external means. It can flow through protected, enclosed channels from one place to another. This idea wasn't entirely new. Industrial machinery had been using enclosed shaft systems for decades in factories. But could this concept be adapted for the rough, unpredictable world of farming? Enter the power take, off, often abbreviated as PTO. This device would become the backbone of modern agricultural efficiency. But what exactly makes it so special? At its core, the PTO is deceptively simple. It's a rotating shaft that extends from the tractor, spinning at a standardized speed, ready to deliver power to any compatible implement. Think of it as a universal power outlet, but instead of electricity, it delivers mechanical rotation. The genius of this system lies in its standardization and versatility. Once tractors began including PTO shafts, implement manufacturers could design equipment that would work with any compatible tractor. A farmer could attach a mower in the morning, disconnect it at lunch, and hook up a baler in the afternoon. The same power source could drive completely different machines. Why had it taken so long for someone to develop such an obvious solution? The answer involves understanding the messy reality of agricultural innovation. Unlike factories where conditions are controlled and standardized, farms present endless variables. Different crops, different terrains, different weather conditions, different implement requirements. Early PTO systems had to overcome numerous technical challenges. What speed should the shaft rotate? How should it connect to implements? How could it remain safe while still being accessible? The International Harvester Company was among the first to seriously tackle these questions. In 1918, they introduced tractors with a rear-mounted shaft that could power threshing machines. Other manufacturers quickly followed. But here's where things got complicated. Each company developed their own system with different specifications. Some PTOs rotated at 540 revolutions per minute. Others used different speeds entirely. The mounting positions varied. The connection methods differed. It was chaos. Imagine being a farmer in the 1920s or 30s. You might own a tractor from one manufacturer and implements from several others. Would they work together? Maybe, maybe not. You might need adapters, custom modifications, or you might simply be out of luck. This lack of standardization meant that the PTO's full potential remained locked away, tantalizing but frustratingly out of reach. Something needed to change, but who would make it happen? The answer came through cooperation and standardization efforts that began in the 1930s and continued through the 50s. Agricultural engineers, manufacturers, and farming organizations recognized that everyone would benefit from agreed-upon standards. The American Society of Agricultural Engineers took the lead in establishing specifications that would become industry norms. They determined that PTOs should typically operate at either 540 or 1,000 revolutions per minute. They standardized the shaft diameter, the spline design, and the mounting height. Why these specific speeds? The choice wasn't the arbitrary. 540 RPM became the standard because it represented a good balance for many common farm implements. It was fast enough to operate most equipment efficiently, but slow enough to be relatively safe and manageable. The 1000 RPM option came later, designed for implements that needed higher speeds like some mowers and pumps. These standards transformed the agricultural equipment industry overnight. Suddenly, compatibility became the norm rather than the exception. But standardizing the tractor's output was only half the battle. The shaft that connects the tractor's PTO to the implement presented its own set of engineering challenges. This connecting shaft needed to do something rather remarkable. It had to transmit tremendous amounts of rotating power while accommodating the fact that tractors and implements move relative to each other. When a tractor turns, or when ground terrain causes the implement to shift position, the connection between them must flex and adapt without breaking or losing power transmission. The solution came in the form of the telescoping PTO shaft, an elegant piece of engineering that deserves more appreciation than it typically receives. Picture two tubes, one inside the other, connected by splines that allow them to slide in and out while continuing to transmit rotation. At each end, universal joints permit angular movement. These joints work like the ones in your car's drive shaft, allowing the shaft to bend at angles while still spinning. Together, these features create a shaft that can extend, contract, and operate at various angles. How much engineering ingenuity went into making something that farmers could simply connect and forget about? Safety became another critical concern as PTO systems evolved. A spinning shaft carrying enough power to operate heavy machinery is inherently dangerous. In the early days, exposed PTO shafts caused horrific accidents. Clothing would catch on the spinning shaft, pulling the operator in with devastating consequences. Limbs could get tangled, lives were lost. The question became urgent. How could this power transmission system be made safer without compromising its functionality? The agricultural industry responded with protective shields. Modern PTO shafts come encased in smooth, rotating guards that spin freely around the power shaft itself. If something touches the guard, it simply rotates with it rather than catching and pulling. These shields overlap where the shaft telescopes, maintaining protection throughout its range of motion. Regulations now require these safety features, and they've saved countless lives. Yet even today, farmers must remain vigilant, as accidents still occur when shields are damaged or removed. The types of implements that PTOs can power seem almost limitless. Consider the rotary mower, one of the most common PTO-driven tools. The tractor's engine spins the PTO shaft, which turns the mower's blade assembly at hundreds of revolutions per minute. The same principle applies to hay balers, which compress cut hay into compact bales. The PTO drives the complex mechanical systems that gather, compress, and tie the hay, transforming loose fodder into manageable packages. Without the PTO, these operations would require separate engines for each implement, adding weight, complexity, and expense. Post-hole diggers represent another fascinating application. These auger-based tools drill into the earth, creating holes for fence posts. The PTO provides the sustained rotational force needed to bite through soil and roots. Pump systems for irrigation draw water from wells or streams using PTO power. Spreaders distribute fertilizer or seeds across fields with PTO-driven mechanisms that ensure even distribution. The list goes on: feed mixers, grain augers, wood chippers, snow blowers, and dozens of specialized implements for specific crops and tasks. Each one taps into that standardized power source, spinning away at the rear of the tractor. But how exactly does the power travel from the tractor's engine to the PTO shaft? Understanding this reveals another layer of engineering sophistication. Inside the tractor, a series of gears and clutches connect the engine's output to the PTO shaft. Most modern tractors offer independent PTO operation, meaning the PTO can run while the tractor is stationary, or the PTO can be disengaged while the tractor moves. This independence comes from a dedicated clutch system controlled by the operator. Older tractors use transmission-dependent PTOs, where the PTO would only spin when the tractor was in gear and moving. This limitation meant stopping the tractor also stopped the implement, which wasn't always desirable. Imagine trying to bale hay. You want to keep the baler running continuously while you drive through the field. If your PTO stops every time you pause to adjust your position, you lose efficiency and risk jamming the machinery. Independent PTOs solved this problem elegantly, giving operators full control over when implements receive power. The mechanical connection between implement and tractor requires careful alignment and proper installation. Farmers must measure the required shaft length, as using a shaft that's too long or too short creates problems. Too long, and the shaft might bottom out when compressed during tight turns, potentially causing damage. Too short, and the shaft might separate during operation, with catastrophic results. Proper installation also requires ensuring that safety shields are correctly positioned and secured, that universal joints are adequately greased, and that locking pins are fully engaged. Agricultural equipment dealers and experienced farmers know these procedures intimately, but new farmers often learn through trial and error. The consequences of improper installation can range from annoying equipment malfunctions to serious safety hazards. This reality has led to extensive training programs and safety campaigns. Agricultural extension services provide education on correct PTO usage, recognizing that knowledge saves lives and equipment. The economic impact of PTO technology on farming cannot be overstated. Before its widespread adoption, farmers needed multiple power sources for different tasks. A farm might have several small engines scattered across various implements, each requiring maintenance, fuel, and eventual replacement. The PTO system consolidated power generation into the tractor, dramatically reducing costs and complexity. One well-maintained tractor engine could power an entire farm's worth of implements. This efficiency made farming more profitable and accessible, contributing to the broader mechanization of agriculture that transformed food production worldwide. Consider the time savings alone. Tasks that once required days can now be completed in hours. A farmer can mow, rake, and bale an entire field in a single day using PTO-driven implements. Without this technology, the same work might take a week using older methods. Time savings translate directly to economic advantages. Farmers can manage larger operations with less labor. They can respond more quickly to weather conditions, harvesting crops at optimal times. They can diversify their operations, growing multiple crops or raising livestock alongside crop production. The international adoption of PTO standards facilitated global agricultural trade and cooperation. A farmer in Australia can purchase implements manufactured in Germany, confident they'll work with their American-made tractor. This interoperability has created a truly global agricultural equipment market, driving innovation through competition and making advanced farming technology accessible worldwide. How many other industries can claim such successful international standardization? Yet the story of the PTO isn't just about the past. Modern developments continue to evolve this technology. Electronic PTO systems now offer features that mechanical systems couldn't provide. Sensors monitor shaft speed, torque, and power consumption. Automated engagement systems start and stop implements based on GPS positioning or operator-defined triggers. Some advanced tractors can adjust PTO speed on the fly, optimizing power delivery for varying conditions. These digital enhancements build upon the mechanical foundation established nearly a century ago. Hydraulic systems have also influenced PTO evolution. While hydraulics handle many functions on modern tractors, the mechanical PTO remains essential for high-power, continuous operation tasks. Hydraulics excel at intermittent, precise movements like raising and lowering implements or operating cylinders. But for sustained rotational power, mechanical drive through a PTO shaft remains more efficient and reliable. The two systems complement each other, with modern tractors using both extensively. The environmental implications of efficient power transmission deserve consideration too. By enabling one engine to power multiple implements, PTO systems reduce overall fuel consumption compared to having separate engines for each machine. Less fuel means lower emissions and reduced environmental impact. Modern tractors with efficient PTO systems can accomplish more work with less fuel than ever before, contributing to more sustainable agricultural practices. Looking at the agricultural landscape today, it's remarkable to consider how thoroughly PTO technology has been integrated into farming operations. Equipment manufacturers design virtually all tractor-mounted and tractor-towed implements with PTO compatibility in mind. The standardization that once seemed like an impossible goal is now so complete that most farmers never think about it. They simply expect their equipment to work together, and it does. The reliability of modern PTO systems is equally impressive. With proper maintenance, these mechanical connections can operate for thousands of hours without failure. The simplicity of the core design contributes to this durability. There are no complicated electronics or delicate components in the shaft itself, just hardened steel, precision machining, and robust universal joints. This reliability matters enormously in agricultural settings where breakdowns during critical operations can result in significant financial losses. Training the next generation of farmers includes comprehensive education about PTO systems. Agricultural colleges and vocational programs teach students about proper connection procedures, safety protocols, and troubleshooting techniques. Understanding PTOs isn't optional for anyone planning to work in modern agriculture. It's as fundamental as knowing how to operate a tractor or recognize crop diseases. This educational emphasis ensures that knowledge about this crucial technology continues to pass from generation to generation. The diversity of PTO shaft designs reflects the varied demands of agricultural work. Heavy-duty shafts with larger diameters and reinforced universal joints handle high-torque applications like large balers or heavy-duty tillers. Lighter-duty shafts suffice for implements with lower power requirements. Quick connect systems have largely replaced older pin and clip connections, making it faster and easier to attach and detach implements. These seemingly minor improvements add up to significant time savings over a farming season. Maintenance requirements for PTO systems are straightforward but essential. Universal joints need regular greasing to prevent wear and ensure smooth operation. Shields require inspection for damage and proper function. Splines should be checked for wear, and the shaft tubes should slide smoothly without binding. Neglecting these basic maintenance tasks leads to premature failure and potential safety hazards. Most farmers incorporate PTO inspection into their regular equipment maintenance routines. The sound of a PTO shaft in operation has become one of the familiar noises of rural life. That distinctive mechanical whir, varying in pitch as load changes, signals that work is happening. Experienced farmers can often diagnose problems by sound alone, detecting bearing wear, misalignment, or excessive load by the characteristics of the noise the shaft makes. This acoustic feedback provides valuable information about system health. Specialty applications push PTO technology in interesting directions. Forestry equipment uses PTOs to power winches, chippers, and processors. Municipal operators use PTO-driven equipment for everything from street sweeping to snow removal. Construction applications leverage tractor PTOs for pumps, compressors, and other tools. While agriculture remains the primary domain, the versatility of standardized rotational power has found applications across many industries. The relationship between tractor power and PTO capability deserves attention. A tractor's PTO can't deliver more power than its engine produces, minus losses through the transmission and gearbox. Manufacturers rate tractors by their horsepower, and a portion of that power is available at the PTO. A 100 horsepower tractor might deliver 85 to 90 horsepower through its PTO under optimal conditions. Understanding this relationship helps farmers match tractors to implements appropriately, ensuring adequate power without overbuying tractor capacity. Implement manufacturers publish PTO power requirements for their equipment, allowing farmers to make informed purchasing decisions. A large round baler might require 60 horsepower at the PTO, while a rotary mower might need only 35. These specifications guide farmers in building compatible equipment packages. Using an underpowered tractor with a demanding implement results in poor performance, excessive fuel consumption, and potential damage to both tractor and implement. The math isn't complicated, but it's crucial. Climate variations affect PTO operation in ways that aren't always obvious. Cold weather makes lubricants thicker, increasing friction, and requiring more power to spin shafts and implements. Hot weather can cause thermal expansion, potentially affecting tolerances in precision components. Dust and mud can infiltrate connections if shields are damaged. Farmers in different climates develop specific maintenance practices suited to their conditions, demonstrating how agricultural technology must adapt to local environments. The future of PTO technology likely involves increased integration with precision agriculture systems. Already, some advanced tractors can modulate PTO speed based on implement load sensors, optimizing fuel efficiency and work quality. GPS-guided systems might automatically engage and disengage PTOs based on field boundaries or obstacle detection. Electric PTOs driven by hybrid or fully electric tractor systems could offer even finer control and efficiency. Yet the fundamental principle of transmitting rotational power from tractor to implement will likely remain relevant for decades to come. Comparing modern PTO systems to their early predecessors highlights how far the technology has progressed. Early systems were crude, dangerous, and inconsistent. Modern systems are refined, safe, and utterly reliable. Yet the basic concept hasn't changed. Power still flows from engine to shaft to implement through mechanical connection. This continuity demonstrates that the original vision was sound, requiring only refinement rather than reinvention. The standardization battles of the mid-20th century offer lessons for other industries struggling with compatibility issues. When competitors recognize that cooperation on standards benefits everyone, entire industries can advance more rapidly. The PTO standardization process wasn't always smooth. Companies had to surrender proprietary advantages and accept compromises. But the result was a more vibrant, competitive market that better served customers. Similar dynamics play out today in electronics, telecommunications, and countless other fields. Agricultural shows and demonstrations often feature PTO-driven equipment prominently. Manufacturers showcase new implements, highlighting innovative features and improved efficiency. Farmers attend these events to evaluate equipment and learn about advances in technology. The PTO connection is so fundamental that it's almost taken for granted, yet it enables all the impressive capabilities on display. Without this standardized power transmission method, the agricultural equipment industry would look radically different. Small-scale and hobby farmers benefit from PTO technology as much as commercial operations. A small tractor with a 20 to 30 horsepower PTO can power everything a hobby farmer needs. A mower for pastures, a tiller for gardens, a post-hole digger for fencing, even a small baler for livestock feed. This accessibility has made small-scale farming more practical and appealing, contributing to the growth of local food movements and sustainable agriculture practices. The simplicity of PTO operation belies the engineering sophistication that makes it possible. When a farmer pushes the PTO engagement lever, multiple systems coordinate seamlessly. The clutch disengages, the PTO gear engages, the clutch re-engages smoothly, and power begins flowing to the implement. This process happens in seconds, smoothly enough that operators barely notice. Achieving this level of refinement required decades of engineering development and countless incremental improvements. International agricultural development programs often include PTO technology as a key component. Tractors and implements provided to developing regions feature standardized PTOs, enabling recipients to access a global market for equipment and parts. This standardization prevents aid recipients from being locked into proprietary systems that might leave them stranded when equipment needs replacement or repair. It's a small detail that has significant long-term implications for agricultural development success. The story of the power takeoff shaft is ultimately a story about solving problems through engineering ingenuity and industry cooperation. Farmers needed a way to harness tractor power for multiple purposes. Engineers developed mechanical solutions. Industry leaders recognized that standardization would benefit everyone. Together, these elements created a technology that transformed agriculture. The questions that drove early development, how to transmit power safely, efficiently, and universally, found answers that continue to serve us today. Every time a farmer connects an implement to a tractor, they're engaging with a legacy of innovation that spans more than a century. They probably don't think about the engineers who standardized shaft speeds, or the manufacturers who agreed to common specifications. They're focused on the work at hand, cutting hay, drilling holes, spreading fertilizer, or any of countless other tasks. And that's exactly as it should be. The best technology becomes invisible, fading into the background as it quietly enables productivity. The power takeoff shaft exemplifies this principle perfectly. The evolution of safety features surrounding PTO systems represents one of the most important chapters in agricultural equipment development. Early farmers who worked with exposed rotating shafts faced dangers that modern operators can barely imagine. The shaft spinning at 540 revolutions per minute created a blur of motion that could grab loose clothing, long hair, or an errant hand in an instant. What happened next was almost always catastrophic. The human body cannot compete with the rotational force of a tractor engine, and accidents resulted in amputations, crushing injuries, and deaths that devastated farming families and communities. These tragedies sparked urgent conversations about how to maintain the functionality of PTO systems while dramatically reducing their dangers. The challenge was significant. Any safety device had to protect operators without interfering with the system's core purpose. It couldn't add so much weight that it became impractical. It couldn't be so expensive that farmers would skip purchasing it. And it had to be durable enough to withstand the harsh conditions of agricultural work, everything from mud and manure to extreme temperatures and constant vibration. By the way, if you're interested in understanding how great machines were born, the industrial brands that dominated their era, and the technology that drove progress, this channel offers real stories every week that combine innovation, ambition, and mechanical power. Subscribe and discover the secrets behind the machines that move the world. The development of the Master Shield concept marked a turning point in PTO safety. Engineers designed a smooth, cylindrical guard that rotated freely around the PTO shaft itself. The key innovation was that the shield didn't spin at the same speed as the shaft inside it. Instead, it rotated slowly or not at all when touched, dramatically reducing the grabbing risk. The shield was supported by bearings at each end, allowing it to spin independently of the power shaft. If clothing or hair contacted the shield, it would simply rotate gently rather than catching and pulling with deadly force. But implementing this solution required overcoming numerous technical obstacles. How could the shield remain in place while accommodating the telescoping motion necessary for the shaft to extend and contract? The answer involved creating overlapping shield sections that slid within each other, much like the shaft itself. As the tractor and implement moved relative to each other, both the power shaft and its protective shield would extend or compress in tandem. This parallel action maintained protection throughout the full range of motion. Manufacturing these shields presented its own challenges. They needed to be light enough that they didn't add excessive weight, yet strong enough to withstand impacts from rocks, branches, and the general abuse of farm work. They had to resist corrosion from fertilizers, pesticides, and manure. And they needed to be shaped in a way that debris wouldn't accumulate on them, creating balance problems or interfering with their rotation. Material science and manufacturing techniques had to advance considerably before truly effective shields became practical for widespread use. The regulatory environment played a crucial role in driving safety improvements. As accident statistics accumulated and their human cost became undeniable, governments began mandating safety features for agricultural equipment. In the United States, the Occupational Safety and Health Administration established standards for PTO shielding. European countries implemented similar regulations. These mandates created a legal framework that pushed manufacturers to prioritize safety even when it added to production costs. Farmers themselves sometimes resisted these safety improvements, not out of recklessness, but from practical concerns. Early shields could be clumsy and interfered with operations if not properly designed. They added weight to implements that were already heavy. And if shields became damaged during use, farmers working remotely from repair facilities might simply remove them rather than interrupt their work schedule. This tension between safety and operational convenience sparked ongoing dialogue between farmers, manufacturers, and safety advocates about how to design protection that people would actually use. The solution emerged through iterative design improvements informed by user feedback. Modern PTO shields incorporate quick-release mechanisms that make removal and reinstallation straightforward when legitimate maintenance requires it. They're designed with clearances that prevent interference with normal operation. And they're built from durable plastics and metals that withstand abuse while remaining relatively lightweight. These refinements made shields practical enough that most farmers now accept them as essential equipment rather than optional accessories. Education campaigns complemented regulatory requirements and design improvements. Agricultural extension services, equipment dealers, and farming organizations launched initiatives to teach safe PTO operation. These programs emphasized multiple layers of protection. Keep shields in place and in good condition. Wear fitted clothing without loose ends that could catch. Tie back long hair. Never step over or reach across a spinning PTO shaft. Disengage power before connecting or disconnecting implements. Never attempt to clear jams or adjust equipment while the PTO is engaged. These guidelines, simple in principle, but requiring constant vigilance in practice, have prevented countless accidents. The introduction of color coding helped make PTO shafts more visible and therefore safer. Many manufacturers began producing shields in bright yellow, orange, or red. These high-visibility colors serve as constant visual reminders that a potential hazard exists. They make it easier to see the shaft's position relative to the operator's body, reducing the risk of accidental contact. Equipment that might be used in low-light conditions, reflective strips or markings, provide additional visibility. Technological advances brought new safety features beyond physical shielding. Some modern tractors include PTO engagement systems that require deliberate action rather than simple lever movement. The operator might need to pull a lever and press a button simultaneously, reducing the chance of accidental engagement. Warning lights and audible alarms alert operators when the PTO is engaged, providing an additional layer of awareness. These features represent the application of human factors engineering to agricultural equipment, recognizing that preventing accidents requires understanding how people actually interact with machinery. The economic cost of PTO accidents extended far beyond medical bills and lost productivity. Insurance companies began charging higher premiums for farms with poor safety records. Workers' compensation claims related to PTO injuries could bankrupt smaller operations. And the emotional trauma of witnessing or experiencing a serious accident affected entire communities. These broader impacts created additional incentives for everyone involved in agriculture to take safety seriously. Maintenance practices directly impact PTO safety in ways that aren't always obvious. A worn, universal joint might seize suddenly, causing the shaft to whip violently. A damaged shield might not rotate freely, defeating its protective purpose. Loose mounting bolts could allow components to shift during operation, creating unexpected hazards. Regular inspection and maintenance therefore serve dual purposes, ensuring both operational efficiency and safety. Smart farmers develop checklists and schedules for examining their PTO systems, catching potential problems before they cause accidents. The agricultural equipment rental industry faces unique challenges regarding PTO safety. When multiple operators use the same equipment, maintaining consistent safety practices becomes more difficult. Rental companies must ensure that shields remain in place, despite being handled by numerous users with varying levels of experience and care. They must provide clear instructions about proper operation, and they must inspect equipment thoroughly between rentals. These requirements add to operational costs, but are essential for protecting users and limiting liability. Children on farms represent a particularly vulnerable population regarding PTO hazards. Farm families often involve children in agricultural work from young ages, teaching them responsibility and work ethic, while contributing to family operations. However, children may lack the judgment and impulse control to consistently follow safety protocols around dangerous equipment. Many farm accidents involving PTOs have child victims. This reality has led to specific educational programs aimed at teaching farm safety to young people and encouraging parents to restrict children's access to operating equipment until they're mature enough to handle the responsibility. The mechanics of how universal joints function within PTO shafts deserves deeper exploration. These joints, also called U-joints or cardan joints, consist of a cross-shaped piece with bearings at each arm end. The cross connects two yokes, one attached to each shaft section. As the shafts rotate at an angle relative to each other, the cross rocks back and forth within the bearings, transmitting rotational force while accommodating the angle. This elegant mechanical solution has existed for centuries in various applications, but its use in agricultural PTOs demands particularly robust construction to handle high torque and continuous operation. Each universal joint has a maximum angle at which it can operate efficiently. Exceed this angle, and several problems occur. The joint binds and creates resistance. Bearing wear accelerates dramatically, and the rotational speed varies throughout each revolution, creating vibration and uneven power delivery. This phenomenon, called angular acceleration, becomes more pronounced as the angle increases. Manufacturers specify maximum operating angles for their PTO shafts, typically between 30 and 40 degrees. Exceeding these specifications leads to premature failure and poor implement performance. The telescoping sections of PTO shafts use splined connections to transmit torque while allowing linear motion. These splines are precision-machined grooves running along the shaft length. The inner and outer tubes have matching male and female splines that slide relative to each other while maintaining rotational coupling. The splines must be manufactured to exacting tolerances. Too loose, and they'll wear rapidly and create dangerous play. Too tight, and they'll bind rather than sliding smoothly. This precision manufacturing contributes significantly to PTO shaft cost, but is essential for reliable operation. Lubrication of splines and universal joints represents critical maintenance that many operators neglect. The constant sliding motion of telescoping sections generates friction and heat. Without adequate lubrication, metal grinds against metal, creating wear particles that accelerate degradation. Universal joint bearings operate under tremendous pressure and speed. Their needle bearings require regular greasing to maintain the oil film that prevents metal-to-metal contact. Most PTO shafts include grease fittings at each universal joint and along the telescoping sections. The recommended maintenance schedule typically calls for greasing every 8 to 10 hours of operation, though conditions like dust or moisture exposure might require more frequent attention. Different types of PTO shafts serve specialized purposes beyond the standard agricultural applications. Industrial PTOs on trucks and utility vehicles power auxiliary equipment like hydraulic pumps, generators, and compressors. These often operate at different speeds than agricultural PTOs and may include additional features like automatic engagement based on engine speed or vehicle park brake status. Marine PTOs on fishing vessels, power winches, and processing equipment. Even some vintage automobiles included PTO options for operating tire pumps or other accessories. The torque capacity of a PTO shaft depends on multiple factors. Shaft diameter plays an obvious role, with larger shafts capable of transmitting more torque before twisting or failing. Material properties matter too, with heat-treated alloy steels providing strength and durability. The spline design affects capacity as well, with more splines distributing load across more contact points. Manufacturers rate their shafts for specific torque values, and users must select shafts appropriate for their application. Using an undersized shaft risks failure during operation, potentially causing equipment damage or injury. The sound and vibration characteristics of PTO operation provide diagnostic information to attentive operators. A healthy PTO shaft produces a steady, smooth hum without significant vibration. Changes in sound or feel indicate potential problems. A clicking or knocking sound might signal worn universal joints. Excessive vibration could indicate imbalance from damaged shields, bent shafts, or improper installation. A grinding noise suggests inadequate lubrication or bearing failure. Learning to recognize these audio and tactile cues helps farmers identify problems early before they escalate into serious failures. Some modern tractors offer variable speed PTOs that can operate at speeds other than the traditional 540 or 1,000 revolutions per minute. These systems use electronic controls and variable ratio transmissions to provide any speed within a specified range. This flexibility allows precise matching of PTO speed to implement requirements, optimizing both performance and efficiency. An implement designed to operate at 750 RPM can receive exactly that speed rather than being forced to accept a standard speed and use internal gearing to achieve the desired operating speed. This technology represents the cutting edge of PTO development, though its complexity and cost currently limit adoption mostly to high-end tractors. The transition from mechanical to electronic control systems has transformed how operators interact with PTOs. Older tractors used simple mechanical levers directly connected to clutches and shifters. Pull the lever, engage the PTO, push it back, disengage. Modern tractors might use switches or buttons that send signals to solenoid-actuated clutches. This electronic intermediation enables additional features like soft start and stop, where PTO engagement happens gradually rather than suddenly. Soft engagement reduces shock loads on implements and driveline components, extending their service life. It also makes operations smoother and more pleasant for the operator. Monitoring systems on advanced tractors track PTO operation and alert operators to potential issues. Sensors measure shaft speed, torque output, and temperature at various points. If torque exceeds safe levels, the system might automatically disengage the PTO to prevent damage. If temperature rises above normal ranges, indicating inadequate lubrication or excessive load, warning lights and alarms alert the operator. These monitoring capabilities transform PTO operation from a relatively blind mechanical process into one with full visibility into operating parameters. The global nature of modern agriculture means that equipment standardization extends beyond physical dimensions to include regulatory compliance across different jurisdictions. A tractor manufactured in Germany for sale in Australia must meet Australian safety standards. An implement made in the United States for export to Brazil must comply with Brazilian regulations. This international regulatory complexity has generally converged around similar requirements, thanks in part to international standards organizations that work to harmonize rules across borders. The result is that PTO equipment can move relatively freely in international trade, benefiting farmers worldwide with access to diverse, competitive equipment options. Training simulators have emerged as valuable tools for teaching safe PTO operation without the risks associated with real equipment. These simulators use virtual reality or computer displays to recreate the experience of operating tractors and PTO-driven implements. Trainees can practice connecting implements, engaging PTOs, and responding to various scenarios including equipment, malfunctions, and emergency situations. The simulators can introduce dangerous situations that would never be created with real equipment for training purposes, allowing learners to experience the consequences of unsafe practices without actual risk. As this technology becomes more affordable and sophisticated, its use in agricultural education will likely expand. The relationship between PTO shaft length and universal joint angles requires careful consideration during installation. When a shaft is fully compressed, meaning the telescoping sections are pushed together as far as possible, the angles at the universal joints should not be at their maximum. Similarly, when fully extended, the shaft should still have overlap in the telescoping section and reasonable joint angles. Achieving this ideal requires selecting the correct shaft length for each specific tractor and implement combination. Many shafts can be cut to length during installation, but this process requires precision tools and careful measurement to ensure the internal splines aren't damaged. Environmental conditions dramatically affect PTO shaft lifespan. Equipment operating in dusty conditions, such as during grain harvesting or in arid climates, experiences accelerated wear as dust particles infiltrate bearings and splines. Moisture from rain, dew, or working in irrigated fields promotes corrosion, particularly if shafts aren't cleaned and dried after use. Chemicals from fertilizers and pesticides can degrade seals and attack metal surfaces. Farmers in harsh environments often implement additional maintenance procedures such as more frequent lubrication, regular washing, and protective coatings on vulnerable components. The used equipment market for PTO-driven implements is vast and active. Farmers regularly buy and sell used equipment, taking advantage of the standardization that makes a decades-old implement compatible with a brand-new tractor. This equipment longevity and interchangeability benefits smaller operations and beginning farmers who cannot afford new equipment prices. However, buying used equipment requires careful inspection, particularly of PTO shafts and connections. Worn splines, damaged universal joints, and missing or broken shields are common issues with used equipment. Smart buyers either inspect thoroughly themselves or hire knowledgeable mechanics to evaluate equipment before purchase. The physics of power transmission through PTO shafts involves principles that fascinate engineering enthusiasts. Power equals torque multiplied by rotational speed. A given PTO might deliver 100 horsepower at 1,000 RPM or the same 100 horsepower at 500 RPM, but the torque would differ by a factor of 2. This relationship means that lower speed PTOs must handle higher torque for the same power output, requiring more robust construction. The engineers who design these systems must balance multiple competing requirements: strength, weight, cost, and compatibility with existing standards. Retrofit markets exist for adding PTO capability to tractors that didn't originally include it or for upgrading existing systems. These conversions range from relatively simple installations on tractors designed to accept PTOs but not equipped with them, to complex modifications involving custom fabrication and significant mechanical work. Some vintage tractor enthusiasts undertake these projects to expand their tractor's capabilities while maintaining historical authenticity. The availability of retrofit parts and expertise varies considerably depending on tractor make, model, and age. Before we finish, remember that we created this channel with one purpose in mind: to rescue the stories of heavy machinery that reveal how engineering, hard work, and industrial vision shaped our modern history. Because understanding these machines means understanding progress, human effort, and their impact on the world. Subscribe and become part of this community that loves to discover the secrets of the industrial past. The acoustics of PTO operation, while perhaps seeming like a minor detail, actually matter more than many people realize. Excessive noise from PTO equipment contributes to operator fatigue and can cause hearing damage over time. Manufacturers have worked to reduce noise through better bearing design, improved balance, and sound dampening materials and shields. Operators can protect themselves with hearing protection, but reducing noise at the source benefits everyone in the vicinity and makes the work environment more pleasant. Seasonal variations in PTO usage patterns characterize most farming operations. Spring might see intense PTO use for tilling, planting, and fertilizer application. Summer brings mowing and hay production. Fall demands harvesting equipment. Winter might involve snow removal or maintenance work. This cyclical pattern means that PTO components experience periods of intense use, followed by storage. Proper preparation before storage, including cleaning, lubrication, and protection from the elements, helps ensure equipment remains in good condition for the next season. Many farmers who neglect this preparation face corroded bearings, seized splines, and other problems when they attempt to resume operations. The spare parts ecosystem supporting PTO equipment is extensive and sophisticated. Bearings, seals, shields, yokes, and complete shaft assemblies are available through dealers, online retailers, and specialty suppliers. This part's availability is crucial for farmers who need to repair equipment quickly during critical operations. A broken PTO shaft during harvest season can cost thousands of dollars in lost productivity if crops miss their optimal harvest window. Having spare parts on hand or being able to obtain them quickly from local dealers makes the difference between a brief inconvenience and a serious setback. Custom and specialty PTO applications sometimes require unique solutions beyond standard equipment offerings. A farmer developing a novel implement might need a PTO shaft with unusual specifications. Industrial users adapting agricultural PTOs for non-farming purposes might need custom lengths or connection types. A network of machine shops and fabricators serves these needs, creating one-off solutions or small production runs of specialized equipment. This flexibility demonstrates how standardized interfaces enable innovation by making it easier to develop new applications that can interface with existing systems. The future trajectory of PTO technology remains vibrant despite the system's maturity. Electric tractors present interesting questions about how to implement PTO functionality without a mechanical connection to an internal combustion engine. The solutions might involve electric motors directly driving PTO shafts, with electronic controls providing the necessary speed regulation and power management. Alternatively, hybrid systems might maintain mechanical PTOs powered by engines while adding electric drive for vehicle propulsion. These developments are already underway in prototype and limited production tractors, pointing toward a future where PTO capability remains, but the implementation details evolve significantly. Autonomous tractors represent another frontier where PTO technology must adapt. If tractors operate without human drivers, implementing robust safety systems around PTOs becomes even more critical. The machine cannot rely on human judgment to avoid hazards or respond to problems. Instead, sensors and control systems must monitor operation continuously and respond appropriately to any anomalies. This requirement is driving development of sophisticated monitoring systems that will likely eventually migrate back to conventional, human-operated tractors as well. The story of the PTO shaft ultimately reflects broader themes in technological development. A fundamental problem existed: how to efficiently transmit power from tractors to implements. Engineers developed elegant solutions based on sound mechanical principles. Industry cooperation established standards that maximize the benefits for all participants. Ongoing refinement improved safety, reliability, and functionality. And the technology adapted to changing conditions while maintaining compatibility with its past. These patterns repeat across many technologies, but few examples are as clear or as successful as the humble power takeoff shaft that continues to enable productive agriculture more than a century after its invention.